Right, can you see this?
Yes.
Okay.
Okay. So now it's the turn of Ignacio Reyes, who will talk about quantum information for free field. So thanks a lot, Ignacio.
Okay, thank you for the introduction, and thank you to all the organizers for the invitation. It's a pleasure to talk here. So indeed, today I'm going to talk about something very simple. We're going to look at some aspects of quantum information for free field theories in 2 dimensions. So here's the outline. And since we were asked to sort of target the students as well as the researchers, we're going to start with a mostly review introduction, some very basics about the idea of entanglement in case someone is not familiar. And then we're going to review some very well-known universal result. And then we're going to jump into the specific thing I want to talk about today, which are free theories and 1+1 dimensions. I'm going to show you a set of mathematical tools, which is essentially holomorphic calculus, so very standard things, but that turn out to be surprisingly powerful to solve some of these problems completely. And at the end, I want to tell you about an application that we've been working lately, which is a story of moving mirrors in flat space and how you can extract an exact page curve from that physics. And then we're going to finish with some summary and outlook. Okay, so let's start reviewing some very basic notions of entanglement. Entanglement is essentially the question of whether we can specify, if we have a quantum system that has subsystems, can we specify the state of the subsystem, say A, independent of that of the system B? So let's consider for now pure states. And then the 2 usual examples are that if our wave function, if the total wave function for the system is a product state, then of course we can talk about the state of the particle A, say the spin A, without making reference to the state of the system B. Whereas if we have a Bell pair or an EPR pair, we cannot talk about we cannot do this, what I just said, because then we say the 2 particles are entangled. Now, this typically the calculation that you're interested in is when you start from some global state, which might be pure or might be mixed. In this case, again, it's pure. You want to compute the reduced density matrix. The definition of that, if we want the reduced density matrix on the subsystem A, means that we trace out over the Hilbert space defined on the subsystem B. In this very simple example of the 2 qubits, we would take our density matrix, which in this case would be a 4x4 matrix, and we would sum over the states of the second qubit, and that's going to give us some 2x2 matrix, which describes what you can do. It describes the results of measurements localized only on A. Now, again, in this example, if you do this simple exercise, for the case of the pure state, this product state, the reduced density matrix is going to be a diagonal. It's going to have a 1 and 1 in one entry and a 0 in the other one. It's going to be pure, whereas the density matrix for the EPR pair is going to be proportional to the identity. And it's going to be mixed. So one way to quantify the entanglement between these 2 parties, A and B, that is the most common one, is to compute the entropies. So for a classical probability distribution, the Shannon entropy is simply defined as minus the sum of P log P. So then in the case of that we're doing quantum mechanics, you basically do the same calculation, you diagonalize the density matrix, and then you try to compute the trace of rho log rho for the reduced density matrix. Again, in the example above, if you calculate for the product state, the unentangled state, you calculate the entanglement entropy of the subsystem A, the first qubit, you're going to get 0. Whereas in the case of the EPR pair, you're going to get log 2. So that log 2, every time you see a log 2, it's telling you that more or less there is one Bell pair shared between the two subsystems. Now, this was a very simple case of a finite dimensional Hilbert space. Now, we're going to be interested in quantum field theories. And of course, in that case, the matrices are infinite dimensional. So doing this calculation of taking the trace of rho log rho is much more difficult. So we have to provide some method to define the problem and then to try to do a calculation. Now, as a very short detour, and this is not very much related to what I want to say later, but anyways, I couldn't talk about entanglement entropy without mentioning holographic entanglement entropy, which I'm sure is going to appear many times later in this workshop. In that case, there is a prescription for holographic CFTs in which you can calculate this entanglement entropy of some subregion on the boundary CFT by simply calculating the area of some codimension 2 extremal surface in the bulk. And that gives you the leading order. If you're taking the G Newton, so the gravitational coupling, very small, that means this first term is the leading contribution. And then there are sub-leading contributions. And for example, the 0th order in the gravitational coupling is the entanglement entropy, but now not the entanglement entropy of the boundary theory, but rather the entanglement entropy of the bulk quantum fields that live in this region that is somehow like enclosed by the between the RT surface and the boundary. And some of the things we're going to talk about later are actually related to the second term over here. Okay, so now there are many views, many things we can say, many ways to measure maybe entanglement. So one that is very important are called the Renyi entropies. The Renyi entropies are a 1-parameter family of generalizations of the entanglement entropy. They carry a principal and integer index n, and they are defined in this way. So they involve taking the trace of powers of the reduced density matrix. And this has the property that in a certain limit, if you can define a suitable analytic continuation in n, when you take n to a specific value of 1, then this reduces to the entanglement entropy. Now, there's other measures, like for example, relative entropy, which is a comparison between 2 probability distributions, or 2 density matrices. You're trying to see how different they are. It's something like a measure between distance between 2 density matrices. Then if you ask people, say maybe more in the axiomatic quantum field theory community, they might be interested in computing what's called a modular Hamiltonian, which is nothing but the log of the density matrix. Or they might be interested in computing the modular flow, which means take whatever operator you're interested in and then do time evolution to that operator, but not with the physical Hamiltonian that defines the theory, but rather with the modular Hamiltonian. So you're conjugating here with the density matrix, and that defines a flow that has a lot of nice properties, and you can study that. Now there's many other measures or views or things you can talk about: entanglement purification, squash entanglement, etc., etc. But these are some of the most common ones in this area. Okay, so just to give, since we were asked to provide a bit of review, I'm going to go through a quick reminder of a very well-known result, which is the entanglement entropy for a single interval on the vacuum of a CFT in 2 dimensions. So the idea is the following. Well, first I have to tell you what I want to compute. So the ideas are universe has 2 dimensions, time and space here. And the idea is that quantization happens at equal time, right? You have to foliate the space-time with slices that you're going to call constant time, which is here, this dotted line. And that defines a density matrix, a global density matrix, for a given time. And then the idea is that we want to trace out, we want to choose some region, in this case, this interval A, and we want to trace out the rest of the real axis, which is what I'm calling B. It's the complement of A. That defines a reduced density matrix for each time. And for that reduced density matrix, you want to calculate, say, the entanglement entropy. So how are we going to do that? Well, first we say, let's calculate the Renyi entropies. And one way of doing that, which is very well known, is using the so-called replica trick. Now, the replica trick is simply a sort of geometric way to set up the problem of computing the trace of the power of the density matrix. So suppose the density matrix has two indices. Let me call them here. It's these sub-indices over here. So the idea is that if you take the nth power of the density matrix, you're going to have you're going to have n times rho here, in which you contract the columns of one matrix to the rows of the other one. So the second index here is always going to be matched to the first index of the next matrix, and then the second one here is going to be matched to the first index in the other matrix, and so on and so forth. Until you get to the very last term, we have n terms in total. And because you're taking a trace here, this should be cyclic. So the last index has to be matched to the first index, and then you sum over all the indices. Now, if you're doing field theory, a pictorial way or a geometric way to set up that calculation is to take n replicas of your original manifold, which is the one that is in the first picture, in the first figure. You copy it n times, and then you glue these manifolds in a cyclic way, exactly in the same way as this formula is telling you. So you open a small slit around each region, the region you're interested in, and then you glue the upper lip of this slit to the lower one and the next one, and so on and so forth. And finally, you connect, you do the same thing with the first and the last copy, because this thing should be symmetric. So once you have that thing, you're supposed to compute a partition function on that manifold, but that is kind of confusing. So what we do is you take this complicated geometry that has many sheets, and you make a conformal transformation that sort of unwraps this funky surface and brings it back to one copy of the original spacetime, which is this last picture here on the bottom. Now, when you do that, you have to pay a price because you had to unwrap this complicated surface. And the price you pay is that you have to introduce on the endpoints of the slit, you have to introduce what's called a twist operator, which is shown in these, depicted with these blue dots over here. Now, if you're not very familiar to twist operators, this is very easy to understand. And it's the same thing that happens if you cut and glue, which is the same, it's essentially what we're doing. When you cut a circle and you glue in order to get a cone. So if you start with a perfect disk and say you cut here, you have a sort of a Pac-Man shaped figure. And then when you identify these two edges, you know what you're gonna get, viewed from 3D, you're gonna get a cone. So that cone is sort of smooth everywhere except at the tip of the cone. So you can pretend that the cone is a disk, but you have to pay again the price that you have to put some specific operator there in the middle that remembers you of what the fields are actually doing over there. It remembers that you actually did a cutting and gluing operation. So these are these twist fields. And the statement is the following. If you have a single interval, if you're interested in a single interval and your global state is a vacuum in 1+1 dimensions of a conformal field theory, then the nice thing is that the entanglement entropy, when you actually do this calculation of the Renyi entropies, you take the limit, this turns out to be, to depend on, it's determined by the 2-point function of these twist operators. And it turns out that conformal symmetry tells you what the answer is. It fixes this 2-point function because these are primary fields. And when you run the calculation, the result that you get is this thing over here. The entanglement entropy is the central charge over 3 times the log of the distance between the two twist fields, so the endpoints of the region, divided by some UV cutoff, which I don't want to get very involved into, but it has to be there because actually the entanglement entropy is not well defined. It's not something that you can actually make sense of. It's UV divergent, so you have to regulate it and put some cutoff over there. So this is a very well-known result, and it's great, it's awesome. The only problem is that it is quite hard to generalize this argument to more interesting cases. So you can do a couple of more things, like solve the problem on the cylinder for a single interval. But as soon as you try to do something more interesting, like taking multiple regions, or taking excited states, or looking at the problem in non-trivial topologies, then this method and the standard CFT tools are not really gonna be very useful. So once we're at this point, we have to make a choice. Say if you want to do research, you have to decide whether you're going to try to say less things, but about a very general set of theories, in which case you would probably try to keep making progress using conformal symmetry, trying to bootstrap stuff and so on, or use some other techniques like holography, for example. That's one option. The other option, which is the one we're going to talk about today, is to say much more about some very specific set of theories. So we're not going to make a big statement about general theories. We're going to make as much progress as we can in a very specific theory. Now, two cases that have been discussed and worked out quite a lot recently are of course, the free theories, the free boson and the free fermion. And I'm going to focus on the second one, on the fermions. And basically the goal will be to find essentially the reduced density matrix itself. And then we can do several computations. So what can we do in free theories here for the fermion? So again, as a sort of review, if we're in 2 dimensions, then we can start with the standard Dirac action. So here the gamma matrices are going to be essentially some Pauli matrices. These are going to be vectors or spinners with 2 components. And it turns out that if the system is massless, then once you decouple the 2, I mean, if you write down the Lagrangian, it separates into the 2 components. So you can just, 2 chiralities. So you can essentially just keep one of the chiralities and forget about the other one for a while. So that's the theory.
Sorry, Ignacio?
Yeah.
I think there's a question in the chat. I don't know if Danilo can unmute himself. Otherwise, I will read out loud his question.
Okay.
He says, what was finally the n dependence of Renyi entropy for the interval?
Sorry, for the Renyi entropy for?
What's the dependence on n of the Renyi entropy for the interval?
Right, so I didn't, so here I just showed you, let me get back to that a bit later, because I don't know if I have the formula, but in the particular case we were looking at, over here, the Renyi entropies are going to have some simple dependence, which goes like something like n plus 1 over n or so. So it's something simple. It's a prefactor. There are some subtleties related to the constant terms, but the term that goes with the C over 3 is a very simple factor depending on n. Okay, now so back to the free fermion, whatever state we look at, the first thing we know about this theory is that the 2-point function for coinciding arguments, when the arguments are very close, has to have a simple pole of this form. So usually we think of the propagator as a number, but here we want to think about it as an operator acting on functions. And the way how it acts is simply by matrix or function multiplication. So if you have some smooth, trial function G, then you define the action of the propagator on that function simply by essentially contracting these two indices and summing, which is doing an integral over some region that we're going to specify later. So every time you see this dot here between two functions, it means that we're multiplying them in this way. So, of course, one thing that is very important to do is once you have an operator, you have to find the spectrum. So you can solve the eigenvalue problem here. Lambda are the eigenvalues of the correlator G. And it turns out that you can solve that problem and the eigenvalues lie in the interval 0, 1. Okay, so that's something important to know. So now what are we interested in doing? We want to compute some reduced density matrices. Now it turns out that because the theory is free, finding the reduced density matrix is equivalent to, you just need to find an operator that reproduces this equation, so that it gives you back the correlator for 2 points, of course, living in the subregion of interest. So here, when in quantum field theory, we have the real line, we fix some time, we're going to choose some region here, and we need to find an operator, rho, that reproduces the correlator in the region. Now, it turns out that in this case, K, which is this modular Hamiltonian, is a quadratic operator because we're going to focus only on Gaussian states. And this, so the log of the density matrix, which is what we define as the modular Hamiltonian, then is, again, it's quadratic with some specific kernel, this small k over here. And it turns out, moreover, that that specific kernel you can read from the 2-point function as an operator. So the punchline here is that if you want to know the reduced density matrix, what you need to compute is the log of, you need to calculate this operator, which is the log of the inverse of the correlator minus the identity. Now you have to remember that this is an operator. So the question is, how do you, given an operator, how do you compute some function of it? And there's a very well-defined technique to do that, which is called the method of the resolvent. So the idea is that you simply use Cauchy's integral formula. So if you want to compute a holomorphic function of an operator, then, well, one thing that you need is that the spectrum of the operator lies in some compact subset of the complex plane. So all the eigenvalues should be like in some compact region. If you have that, and you have some holomorphic function f, then you can define the function of an operator simply by using Cauchy's integral formula, which is true because it is true for every eigenvalue. So given this function f, you simply have to do a contour integral over some contour gamma that wraps around the entire spectrum. And here you have to put this pole lambda minus g. This thing, lambda minus g, is defined as the resolvent. It's what we're calling R here, and it satisfies this equation. So it's simply the inverse of lambda, which is a complex number, times the identity minus g. So if you find this resolvent, then you can go back and do these contour integrals and get whatever you want, what you're interested in. So here's a recipe of how to find this operator. So the first thing you do is the resolvent, you separate in two pieces. This is just a change of variables. There's nothing special happening here. You have the identity, and then you have another piece that we're calling f, which is just makes the equations a bit simpler. So when you write this equation, which is the equation that defines the resolvent in terms of f, you get, if you simply plug this back in this equation, you get this equation. So it has a contribution of f and a contribution of g, and then the product, this matrix or function multiplication of f and g equal to 0. So that's a completely well-defined mathematical problem. And in principle, you could ask someone just to solve it, because you know what G is and you're trying to find f. Now there's a trick that works very nicely to solve this equation. So this equation, I'm rewriting it here, and I'm writing it here explicitly. This is literally what this equation means. You have a function of two variables that you want to find. You have this correlator, and then you have this convolution of these two functions. This has to be equal to 0. So the trick is to recast this integral equation as yet another residue problem in another complex plane, which has nothing to do with the complex integral, the contour integral that we were talking a second ago. And this was the strategy that that we used. The idea is you need to find a function f on the complex plane now, not just in the interval, the complex plane, such that this equation that we're trying to solve is identical to a contour equation. If the left-hand side of these two equations are the same, then you solve the contour equation. You find then you can use some other, then it's sort of easy to guess what the solution is simply by looking at the residues. So there's a recipe to do that. So the idea is that you're now in the complex plane, you have your entangling region here in orange, and you want to make that this contour integral around this big contour gives you back this equation over here. So the answer is the following. I mean, we know that G, the correlator, has a simple pole for the fermion. That's what we said before. If this has a simple pole, then if you deform this contour, the single pole of G is going to produce the first term of this equation. It's going to spit out an F because of the Cauchy integral formula. So then the idea is that in the same way, if F has a simple pole, that's going to spit a term G, which is the second term in this equation. That would explain the first two terms. Now, how would you get the last term by deforming this contour? Well, that means that you need a very specific branch cut, because once you deform this contour, you see you're going to be doing a contour integral around the region. If this does not have a branch cut, that integral is going to vanish, and you're never going to get the third term in this equation. So then there's a specific condition you have to put on the branch cut of this function f, such that things conspire and the contour integral becomes equal to the integral equation. So there are some set of rules that I don't want to specify very much here, but the point is that you can make this problem mathematically very precise, and we solve that problem. And you can find the answer. I'm not going to tell you what the answer is. It's not so important. What is important is what you can do once you have that answer. And that's sort of like having, you know, like the one ring, Sauron's ring, right? When you have that thing, then everything else follows. You control all the rest of the calculations. Once you have the resolvent, you simply, for whatever function you want, give me the function f, I plug it back here, I do the contour integral, and we're done. And that's basically what we did. So you can compute all the Renyi entropies analytically. So here's the quantity you're interested in, and here's the function you have to take. For the Renyi entropies, it's just this particular function. If you want to compute the modular Hamiltonian, this is the function you have to plug back in. Something that we did recently is to compute the modular flow. This is for the experts, probably. They know how hard it is to do these computations. And we did it for a very general case for this problem. And we also showed, well, we found what that function is, and we of course plug that back in. We did the integral, found the explicit results. So the last thing I want to mention is how do you get a page curve from this story? So just a very quick reminder of what the page curve means, and well, at least in the context of black holes, the idea is that there's a black hole that is evaporating, and you're trying to compute the entropy of the radiation as a function of time. And of course, if you do the standard Hawking's calculation, then the entropy that is collected by these partial Cauchy slices that move into the future just keeps growing as the black hole evaporates. And of course, it was mentioned, I mean, this was of of course, this is a problem if this is the whole story, because when the black hole finally evaporates, then you would be left with a mixed state, and the black hole could have collapsed from a pure state, so that would be a problem. So then Page suggested that actually this should not be the whole story, but you should also keep track of the entropy of the black hole. And the expectation is that the correct curve should be the so-called Page curve, which is a curve that goes up and down and is always bounded by these two entropies. So how can we study that in this particular case? And that's part of our work in progress. Instead of looking at black holes, you can look at the physics of mirrors that move in space-time. So you introduce a boundary with some reflecting boundary conditions. In this particular case, it's moving on a Rindler trajectory. And what is super nice is that you can, for the free Fermi, you can do the calculation explicitly. You can compute the Renyi entropies, you can compute the modular Hamiltonian, the modular flow, etc., for any number of regions that you want on any Cauchy slice. And what happens here, the sort of physical intuition is that, for example, if the mirror is accelerating, if it's moving towards you, then it's going to be creating particles, it's going to create entropy. It's associated to a sort of a blue shift in the waves that are reflected back. Whereas if it's moving backwards away from you, it's going to be annihilating particles, lowering the entropy, and so on. And we can obtain the exact Renyi entropies. And as I said before, the interesting thing here is that we can do this for an arbitrary mirror trajectory. So finally, just to give an example of how this works, so if you consider the Penrose diagram of this problem, so you have this mirror moving along some causal trajectory, and the physical region is everything to the right. As I said, we can compute everything on an arbitrary region on some Cauchy slice. But in particular, you can measure, for example, the entropy of the entire slice, which would be this thing over here, for example. And you can calculate its Renyi entropy, say. And a very interesting property is that you can check this explicitly. If the initial and final position and velocity of the mirror are the same, then you can prove that all the Renyi entropies of the initial state are equal to those of the final state. But if all the Renyi entropies are the same, it means that the two density matrices have the same eigenvalues, which means that they are related by a unitary transformation. And you can actually calculate this unitary transformation. So this is a very concrete example where you can guarantee that you have unitarity. And therefore you can calculate the Page curve. You simply follow the entropy as the mirror evolves, and you get something that's going to look like this. So the initial entropies, the Renyi entropies, not just the entanglement entropy, but all the Renyi entropies will end up at the same value as they started. Now, I just want to point out that the final and initial states can be extremely different. So the idea is that if you now take another trajectory that has, again, the same initial and final position and velocities as the first trajectory, then you're going to get some other Page curve, but they will have the same initial and final Renyi entropies. So now in particular, if you want to mimic a black hole, you have to just choose a specific trajectory, but we can do this for arbitrary trajectories. Okay, so just to summarize, there's a lot of new perspectives and insights that you can gain by looking at quantum field theory from this more quantum information point of view. Then I told you how for free theories, it's amazing how much progress you can do by using these complex analysis tools. And finally, I highlighted this thing that you can actually study unitary Page curves from these moving mirrors in flat space. So there's a lot to explore. And if anyone has questions, I'm happy to discuss. Thank you very much.
Thank you, Ignacio. Are there any questions? Well, if, I'll ask. So in order to understand a little bit more this analogy of the moving mirror with black holes, so is the trajectory of the mirror thought as the horizon, or what? I didn't get that.
Well, yeah, so not exactly. So if you wanted to have something like a black hole, for example, I think the horizons would be more similar to, take this example, for instance. Here, this mirror is moving along a trajectory of constant proper acceleration. So here you could take an orbit that goes very close to this mirror and then does something different. And I think a way of thinking about it is that the horizon is that point in space-time where there's somehow like an accumulation of light rays. Like if you come from, null past infinity, there's going to be like a width of like a finite width that ends up in a, we need to draw this to explain it, but there's a finite width in past null infinity that ends up in an infinite width in the future Penrose diagram. So that region would be, for example, somehow analogous to this null surface over here, because there are many, many light rays that end up here, or maybe let me go here. Well, it's not very clear. But I think anyways, the analogy is not exact. It's not like the mirror is the horizon. I think the horizon might probably be more analogous to these null rays here in this particular Rindler trajectory.
Okay, well, maybe we can talk about it later because there are more questions. First, I think Raul had a question. I see his hand is raised.
Hi, Nacho.
Hi.
Now, just a quick question. When you use an ansatz for the resolvent, why that ansatz?
Yes. So
why 1 over lambda square and not lambda to the 10th, for example?
Oh, no, yeah. No, that's not really important actually, because if you, I'm not writing lambda here, the dependence of f of lambda. The only reason why you choose this, so first you want to separate the resolvent into these two pieces. Now the first term here, its purpose is to cancel the identity on the right-hand side, because that identity is not a 1, it's a Dirac delta. It's a very, it's a distribution, right? So that explains this first term. Now the second term over here, having this lambda squared over here, it just implies that there's going to be a lambda over here. You could choose something different and there would be a different coefficient over here.
Okay.
It's not really important. This doesn't mean anything because you still have to solve for f. If you choose another power here, f is also going to change.
No, okay. But the contour integral that you are going to obtain is the same.
Yes.
Thank you.
Okay, there are more questions. I don't know if they want to unmute themselves. Carlos Berciri.
Hey, Ignacio. Nice talking.
Hey.
Just one thing, like, what does it change if I consider free bosons? You get like a higher pole, that's it? Or no? Like, what's the big deal of the free fermion? What's instead of like comparing with bosons?
Yeah, so for the free boson, actually, I think what you have to do is to work with the current because that's the field that is sort of well defined. So you can work with the derivative of the boson, and in that case, the pole is going to be similar, but the see. Actually, yeah, I don't have a really good answer for that. I mean, I know what you have to do is to look at the current, not at the boson itself. Also, if you just look at the boson itself, the propagator is going to have a log. That's going to have another branch cut, so that's going to be a more complicated problem. But what I know there are more complications when you look at the scalar, but I'm not very familiar with that. Actually, maybe Raul can answer that.
Yeah, but I missed the question. In fact, what was the question? Which is the problem with bosons?
Yeah.
No, with the chiral boson, the problem is that you have. I mean, I know this program not in terms of the resolvent, but in terms of the eigenfunctions of what he called G here, of the correlators. And for the fermions, you have just one set. For one interval, you just have one set of eigenfunctions. But for the chiral scalar, you need because this G for the chiral scalar is not Hermitian, and then you need left and right eigenfunctions. And this complicates the things. It's more involved because of that. And when you have more intervals, you have more and more eigenfunctions, left and right.
Ah, okay.
And then at the end, you have to solve a lot of equations. I mean, we did it. It's not impossible, but it's more involved. And as you say, for the normal scalar, you have infrared divergences, and then does not have sense to compute the entropy by itself, let's say. I don't know if the question was that.
No, yeah, I see. Thanks. Thanks a lot.
There's another question by Gabriel.
Hi, Ignacio.
Hey.
Thank you for the talk. I was just wondering if I understood correctly, you used free fermions because, I mean, free theories in general, because things are much simpler and you know the 2-point function exactly. My question is, if you have another construction of another theory and you also know G exactly, does the procedure follow? I mean, like,
I think it depends on the higher point functions. If you can, I mean, I think using a free theory is convenient, not only because you know what the 2-point function is, but rather because you know what the higher point functions are. Because you can use Wick's theorem to bring them down to a 2-point function. In general, you cannot do that.
I understand.
So even if you, in general, just knowing the 2-point function is not enough.
Okay. Thank you.
Well, I guess we can thank Ignacio. Okay, there's a break right now, right? And then discussion session.